Well, our last speaker of the morning is Omri Ben Eliezer, who will be speaking about practical sublinear algorithms for node sampling in large networks. Thank you.
Thank you, Anita, and thank you so much for all the organizers of this wonderful workshop. So I'm going to talk about practical algorithms, still sublinear algorithms. It's in a sublinear regime, but it's a bit more practical than what we saw in the previous talks. And I'm going to make some controversial statements. So for example, I'm going to present heuristics that are unproven. I hope that you will be able to forgive me for this. This is joint work with Talia Eden, Joel Oren, and Dimitris Fotakis. So the problem that we are going to focus on is that of sampling multiple nodes in a large graph, in a large network. We start at a single random node in the graph. And we are only able to explore this large graph through query access. So in each round, we can pick some node that we already saw. And we can query this node and reveal the set of all of the neighbors of this node. So for example, here's one step, and here's another step of our querying procedure. And the eventual goal is to be able to generate many random nodes, or many almost uniform random nodes, using as few queries as possible. Achieving exactly uniform nodes might be hard, so we will be fine with something that is approximately uniform. So we will want to return a random set of k points so that the probability of any particular k points is at most 1 plus epsilon times what we would expect from the uniform distribution. But roughly speaking, just think of it as kind of sampling k, kind of independent, kind of uniform random nodes. And this problem has several motivations. The first motivation is that in many of the access models that we have in our domain, for example, in sublinear time algorithms, probability testing algorithms, and so on, we actually assume access. We assume kind of cheap access to random nodes in a graph. But it might not always be the case that it's easy and cheap to get these random nodes. So if we can only explore the graphs through queries, if it's a graph that, for example, lies in some remote server and we don't have full access to it, then I mean it's just not trivial to get random nodes in the graph. And obviously, there are many algorithms in many other domains that make use of random nodes. More philosophically, it might be useful as kind of a proxy for the problem of kind of exploring many different parts of a network using few queries. So let's say that we arrive at a new environment and we want to explore it and to understand what's going on in this environment. So this is kind of a formalization of this problem. And the last motivation is that these queries, these neighbor queries, are actually supported in modern APIs of real-world social networks, for example, Twitter. You can see here that using the API, you can look up users that follow some other user, and you can look up some which users this specific node, this specific user follows. So we can actually support this neighborhood query that I'm talking about. Okay. So as I said, this talk will be about real-world graphs and about practical algorithms. Specifically, we will talk about social networks. But let's start with some theoretical observations. So the first observation is that there is always a trivial solution. You can always query the whole graph. This will cost n queries if n is the size of the graph. And unfortunately, this is tight in the worst case. So for example, if the graph was the path or the cycle on n vertices, then even to sample one node we actually need to travel an expectation, a linear number of nodes. So this O of n query complexity is tight, even for sampling a single node. Fortunately, many beyond worst case types of graphs, and in particular, many types of graphs that people see in practice, have some better spectral properties. And random walks can be a good solution for these type of graphs. Here I'm talking about, let's say, uniform random walks, although the discussion is relevant to many other types of, many other variants of random walk based algorithms. So this is basically the most standard kind of algorithms that people use in practice for this kind of problems. These algorithms, so some of the most popular variants were analyzed in a paper by Ketty, Gupta, Kumar, Latanzi, and Charlos. And they were able to show that to generate one nearly uniform node in this model, we need to make something like the average degree times the mixing time of the random walk times some mild dependence in the proximity parameter. So this is the number of queries that we will need to make roughly. And it turns out that this is optimal. So there exist graphs for which any algorithm to solve this problem, to sample one nearly uniform node, needs to make almost this number of queries. So the dependence, the multiplicative dependence in both the average degree and the mixing time is tight. And it is actually not hard to show a lower bound of just the mixing time for if you want to sample one node for wide classes of realistic graphs. So for example, we will talk later about core-periphery networks that have kind of a highly expanding core and many isolated components. And for this kind of networks, it's actually not hard to show a lower bound of the mixing time and also a lower bound of k times the mixing time if you want to sample k nodes. And okay, so if the mixing time was small, I mean, for graphs where the mixing time is small, then these kind of algorithms, so random walk-based algorithms, perform pretty well. But it's not always the case, and we will see this soon. And the question that I would like to investigate is whether we can do better than k times the mixing time for realistic graphs for social networks. Okay, so unfortunately, the mixing time can be pretty large. No, it's definitely strongly sublinear. It's not it's not polynomial in it's not as large as the size of the graph, but it can be several hundreds or even several thousands for actual graphs that people see in practice. And there are some theoretical results that are consistent with these observations. So for expanders, we expect the mixing time to be logarithmic, but for some small world models, it's known that it's not logarithmic. It is polylogarithmic though, which is kind of consistent with these numbers. In any case, what we see is that these algorithms will have to make a few hundred queries to generate just one node sample. And this might be not ideal if we want to sample many nodes in the network. So we might want, and this is basically inherent for any kind of algorithm that is memoryless, that each time tries to sample a new nearly uniform node without remembering what happened in the past. However, real-world social networks have other properties that we can try to exploit. So if there is one takeaway message that I would like you to take from this talk is that there are some problems that our first thought would be that we might want to use random walks to solve these problems. So it's not always the case. Sometimes other properties of other kind of structural properties that are maybe not as well known can be as useful or even more useful for these problems. So here we will implicitly or explicitly rely on two properties of large social networks. One property that we rely on, I guess, more implicitly is the fact that they have a parallel degree distribution. So there are many vertices that have much higher degree than others. And another property that we are going to use is the fact that many social networks have a highly connected, highly expanding core. And the rest of the network is consists of isolated periphery components. So I hope with the colors, I hope that you can see this particular example of a core-periphery network. As you can see, the blue nodes in the middle form a highly expanding subgraph. And the green nodes constitute very small components that are connected to this core. Okay, let's try to use the core-periphery structure to see if it can help us in some cases where the mixing time is not that good. So, okay, here is the core-periphery graph. Here's a very, very simple example of a core-periphery graph where the core is just a large clique of size D. And the periphery consists of isolated nodes. So each node in the clique has a single isolated vertex that is connected only to this vertex. And for this graph, mixing time is O of D. But however, there is a pretty simple algorithm that actually samples a uniform node from this graph with a constant number of queries. And the algorithm looks as follows. If we are at the clique, we just travel to a uniform. So we need to figure out which of our neighbors is in the clique, and there is also one neighbor that is not in the clique. So it might take us extra O of 1 queries, but in principle, if we are in the clique, we travel to a uniform node in the clique, and then we decide whether to stay in this node or go to the isolated neighbor. And this is the node that we will return. If we are not in the clique, then we just travel into the clique. So there is an algorithm for this particular graph that samples a perfectly uniform node in this graph in O of 1 queries. It's much less than the O of D queries that we will need using a random walk. And okay, so this is kind of maybe the most basic idea of what we are doing here. There are many technical details, there are many implementation details that I'm not going to go into all of them, but this I think is like the most simplistic picture of what I can say about our algorithm and why it works. Okay, so just a warning, heuristics ahead, not everything will be proved. I hope you will be fine with this. So our algorithm does basically the three following main steps. Maybe you can consider this as two main steps. And one step will be the pre-processing, and the other part will be the actual sampling of nodes. In the pre-processing part of our algorithm, we greedily search for the highest degree for the most influential nodes in the graph, in the network. And using this, let's call this subgraph L0. So this will be the highest degree nodes in the network. And given L0, we can implicitly construct, we can implicitly have a decomposition of the network into several parts. So we have L0. There is L1, which is all of the immediate neighbors of the nodes in L0. And the rest of the graph, L2, will hopefully consist of very small components that are kind of, so they have to, we want them to be very small. We also need them to be reachable in in some sense. But everything relies on the fact that the nodes in L0 are very high degree and very well connected to other parts of the network. So after we greedily search for these L0 nodes, we need to calibrate some estimates we have about the rest of the graph. So given our query model, we will know which nodes are in L0 and which nodes are in L1. We will not know anything about L2, so we will have to do some.
Omri, hey, it's me. So I'm wondering, do you know, given a node, can you figure out if you're in L1, L2, L0? Is there a quick way to know?
Yes, so L0 consists of all nodes that we visited, that we queried. L1 will consist of all nodes that at some point we saw their name when we queried some other node, and L2 is all the rest. Yeah, and after we build L0 and we collect the relevant estimates, we do some calibrations. We will be ready for sampling. So sampling from L0 and L1 will be trivial, and sampling from L2 will be the interesting part of the algorithm. Okay, so the greedy core construction, the first part will be very silly and very prone to adversarial attacks, but it worked for practical social networks. So it could be robustified. I mean, it's but basically the idea is at any given time. So we start with a single node, and at any given time, we visit. We look at all of the neighbors of nodes that are currently in L0, and we add a node that has the highest perceived degree. So, for example, if we start from the left, so all of the neighbors of the first queried node have perceived degree 1, that have one neighbor in L0. So we just pick one of them at random, and then in the second round, there is some node that is a neighbor with 2 nodes from L0, so we will add this one, and so on. So this will be the very simple L0 construction procedure. Again, this is not very robust. If you want to think about a more robust way, maybe to build L0, you can start with a random walk, which kind of randomizes the kind of smooth things. But in practice, it didn't really matter in our experiments. And we actually observed that this collects the highest degree nodes in the network, because social networks in many cases are pretty, I mean, they are very complex in some ways, but they are very simple and in other ways. Now, after we constructed L0, okay, so one thing that is really important for our algorithm to succeed is that we need to choose L0 so that what we think of as periphery components, as isolated components, will actually be periphery components. So we really want L0 to be constructed in such a way that the L2 components are very small. And again, in practice, we observe that this happens pretty fast. So I think we can safely characterize it as sublinear. So for example, this graph, which is seen away, but we will see some results about this graph soon. It suffices to take L0 size of a few tens of thousands vertices, where the size of the whole graph is to the order of tens of millions. So it's pretty tiny. And okay, and once L0 was constructed, we have some preparation to do before we start sampling. So we have some procedures. I'm not going to go into detail, but we have some procedures for estimating the size of L2, which is unknown to us, and figuring out what is how the reachabilities of different components behave. So some reachability, some components will be easier to reach, And if we just sample without any rejection, the distribution that we are going to generate will not be uniform. So we will need to figure out how to do the rejection correctly. And we make some estimates about the reachabilities of nodes in L2. And then after we finish with the pre-processing, we are ready for sampling. And for sampling, so we know the names of nodes in L0 and L1. And we also know the approximate size of L2. So choosing whether to sample from L0, L1, or L2 is straightforward, and sampling from L0, L1 is straightforward. The interesting part is to sample from L2. And this involves, instead of long random walks, as was done in previous works, we just use walks of length 2 that starts at L0 and go to the periphery. And then we run some local BFS in the component that we reach. And most of these components are very small, so the BFS will not be very costly. And this performs remarkably well in practice on some graphs. So as a word of caution, it works well on social networks. It doesn't work well on all types of graphs. Whereas, for example, random walk-based techniques are more generally viable. They could work well on wider classes of graphs. But for example, on Sina Weibo, which is kind of the Chinese Twitter, or sort of a Chinese Twitter, we saw that our algorithm can achieve core complexity per sample that is very, very small. So the basic version of our algorithm reaches something like 5 queries per sample. And this is compared to, let's say, 50, 60, depends on the stage in the process, queries per sample, if you run random walk-based algorithms. And assuming a stronger access model where we don't just see the neighbors, we also see the degrees, we can basically achieve 1 query per sample. So this is kind of the practically optimal result. This is Metropolis Hastings. And this was shown both in our experiments and in previous works to not behave very well in practice. So it's another type of random walk-based algorithm. And we have some results on some other graphs, not as large ones, but still it seems pretty consistent that in many types of social networks, so the red and pink lines are our algorithm, and the others are random walk-based algorithms. And it looks consistent. So the improvement looks consistent in many types of social networks. Again, I must warn that I don't think that the approach will work as well in other types of graphs. So this is the description of the graphs that we looked at and the sizes of L0. So for example, for Sina Weibo, we took, so taking 500,000 nodes in the core, which is less than 1%, was very much an overkill. We could take less, but this is what we took for to generate the results that we've just seen. We also had some results about the generative model, specifically for the forest fire network model. Okay, but I think the most interesting part is to understand why these kind of things work. So we had some, we got some first hint when we looked at the core-periphery simplified graph where we had the click and isolated nodes. But the algorithm is a bit more complex than that, and social networks are definitely more complex than that. So it would be good to at least start figuring out why these kind of algorithms work. First, before understanding why the algorithm works, I want to mention that it provably converges to uniformity if the estimates that we make are good enough. And now I want to explain this part that we've seen before about the fact that the right L0 decomposes L2 nicely. So one observation that we had about social networks that it's kind of related to, so there was some works about the domination number, the size of the minimum dominating set in social networks. We haven't seen exactly a result like this that says the following. For most nodes that have sufficiently high degree, or if you want, you can think about nodes in the K core of the graph or some small k. So for the large majority of these nodes, have some neighbor that has a very high degree. For the highest, for the largest graph that we checked, which is the full tumbler graph, we got that that almost domination performs as good as, so better than all of the other graphs, which I think this kind of behavior shows that there is something sublinear here. So if things seem to behave better in absolute terms when the graph grows, then it's probably because of some sublinear phenomenon. We also have some theoretical bounds on core complexity. I don't want to go into the detail, but we have some bounds that on the core complexity as a function of how the isolated components behave. And let me maybe stop here. I just want to mention some open questions. So as you've seen, we've seen multiple interesting practical phenomena, but I don't think that our theoretical explanations for them are very satisfying at this point. So in particular, I think that explaining and finding more applications to this sublinear almost domination result could be interesting. I mean, what other algorithmic applications can you think of that use the fact that actual social networks have, so the higher degree nodes in the network have a sublinear dominating set? Our access model, our query model, basically queries whole neighborhoods of vertices, and it's a bit strong. It might not be as practical as a model that only relies on random walks. And there are some works on this model. So for example, one work by Issa Shadri and his student about triangle counting. There's not a lot of algorithmic work on graphs that uses the core-periphery structure of social networks. So there are some beautiful works about APSP in real-world graphs that show that APSP is kind of a near linear time problem in these graphs because basically outside the core the tree reads is bounded. So I think core-periphery has more practical algorithmic applications than what we know so far. And also, I think to this end, I think better theoretical guarantees that somehow rely on the core-periphery structure for our algorithm will be interesting. And finally, this algorithm is kind of a learning-based algorithm. So the learning-augmented model usually is more of a streaming model where we see multiple graphs and we learn from earlier graphs and try to exploit some properties of these graphs when we run the algorithm on newer ones. In our case, we kind of learn within the same network, and we kind of optimize our performance using some phenomena that we learn in the same network. But definitely there's much more, there's a lot of room to explore about learning augmented algorithms that behave on real world large networks. So I think the only work that I know of, and could definitely miss some more works, but the only work that I know of is the very recent work about triangle and 4-cycle counting in networks. Okay, let me stop here. Thank you.
Thank you, Omri. We have time for a quick question. Okay, yeah, let me get the front up there. Okay.
Oh, you're going to ask. Okay, thank you for the talk. So you probably mentioned it, but I missed. So in your algorithm, your pre-processing step, after pre-processing, you will know the L0, L1, L2 assignment for each vertex.
Yeah. So we know, as we queried all the L0 nodes, so we know everything about them. We know the names of the L1 nodes because we saw their names when we queried the L0 vertices. They are the neighbors. I mean, the L1 layer is basically all the neighbors of the L0 nodes. And then we don't know anything about L2. So the only thing that we know is that that we haven't seen them, basically.
Good. Okay. So do you have any restriction on the pre-processing time and query?
So I think this is the hardest question of. I mean, yeah. So we have some heuristics. We don't even. I mean, we don't have concrete ways to understand what is the right L0 size. Although I think one thing that one could try is during the construction to try to do sampling, to do the random walks to L2, and to try to figure out whether the components that we reach are small or large. Right. If they are large, so we haven't completed construction. So this is kind of one thing that could be done.
I'm asking this because I'm not sure I 100% get the restriction. So, like if you allow pre-processing, then you probably can do some really powerful things. Like there are ways to divide the graph into like densely connected components and, like isolated vertices, and you can test if your graph are like satisfy your condition that you want or not. And then you can pick the way you want, but this within your model may actually like pay too much than the query complexity actually wants. So yeah, I'm just like, yeah, I think it's probably too interesting discussion for the restrictions on the pre-processing steps. Yeah.
Yeah, so there's a lot of room to explore. I'm not saying that our algorithm is optimal and it also uses. Okay, so I mean, I think one question that is interesting is to understand what can you do with long random walks that kind of learn and kind of calibrate themselves in a better way. If you know that you need to sample many nodes. So the lower bounds that we've seen are for like memoryless random walks. Yeah, so there's a lot of room to explore. I think there's not much work in this area.
Okay, thank you.
Can I ask my question? Okay. Oh. So have you thought about computing PageRank values efficiently? Because it would seem that to solve linear systems on that might be easier if you know the core and periphery.
I'm sorry, could you repeat?
Like if you wanted to compute like PageRank, or you wanted to solve a linear system on the graph, this might help you, right? Because you could basically solve the linear system partially on the core and then like maybe propagate values to the periphery or something.
Yeah, I think it's, I mean, we haven't explored applications that much, but I mean, the obvious next step is to see what this approach can give in related problems. So, and we're actually thinking about it. So we don't have results for PageRank, but we have some preliminary results about other problems that not yet published.
Great. Any other questions? Okay, let's thank Omri again.